Okay, so guys, welcome to Python again, and in this machine learning crash course, we are going to implement linear regression, linear regression model in our Jupyter notebook or Python or Spider or Google Colab that you have. All right, so talking about linear regression, I showed you the basic theory of linear regression in the earlier lecture, and in this we're going to implement it in Python. So first of all, I imported pandas as pd and numpy as np. Alright, then I imported matplotlib.pyplot as plt and seaborn as sns. This is a new command. Probably you had heard of the command sns.set in the earlier machine learning, one of earlier machine learning lectures, or in the FIFA or in the iris, probably in the FIFA actually. So this does the same thing as sns.set, rather it's for matplotlib. What it does, I'm repeating, is that it shows all your data visualizations in the notebook itself and does not open another external web page. Now fine, then we will be performing machine learning or linear regression. We will develop a linear regression model on usahousing.csv. Now, what this usahousing.csv, usahousing.csv is, you can I've sent it to you in the Google Drive. So let me search USA. So there we go, USA. So what do we get? Yeah. So in this is the data set that you have, and it contains 7 columns. It contains 7 columns, 7 to 8 columns, and actually 7 columns it contains, and its respective rows. So let's visualize data to make it more neat. So we grab our pd.readcsv or pandas.readcsv command. Readcsv is something you have to memorize, but you don't want, you can see the documentation, but you don't want to so frequently see the documentation. You have to memorize some commands. So df.head, which gives us the first 5 rows, as I said. Alright, so this is the data neatly arranged. So we have average area income, average house age, average area, average number of rooms, average number of bedrooms, area population, price and address, and as well as the indexes, which is unnamed. So if you get the info of it, we get all the types of the data in each column, which means that it gets the values of the data in each column. For example, we have something called float. What is float? Well, it's decimals. So we have decimals right over here. This is actually float in Python. Float data type. If you want to learn more about data types, see our data types course, data types 1 and 2. So it contains so all these columns, if you see, they are floats because they contain decimals. But is this float? No, I mean, is this float? Well, no, because it is a string, right? It contains characters of alphabets. So address column is a non-null object, which means that it is a string. It's a string object. Alright, so it's non-null because it does not contain any missing data or any in values. Therefore, we don't have to take care of missing data. Description, it gives a statistical description of the entire data in each column respectively, not correlating it with another column. Or a count, so how many values are there? 5,000 values are there in each column. Mean, it returns the mean of each mean of the entire data in each particular column, in each respective column. Actually, that gives a standard deviation, something we are going to talk about in the statistical learning course. It gives the minimum value of each column, or each row in a column, in a particular column. 25 percentile, 50 percentile, 75 percentile, all we're going to do in the statistical learning course. And it returns the max as well. So you'll again observe that this is almost equal to this, which means that 50 percentile is almost equal to the mean. Alright, so df.columns, if you want the columns, you can grab the columns by using this command df.columns. Again, if I do this, it will give an error because it does not support any parameters. It's not an object. Now what we want to do is that we want to get a correlation of the data in each column. So we want to relate the data in each column. So how do we do it? We can create a pair plot. Alright, so what is a pair plot? So we can see different kinds of plots. We can see histogram and we can see scatter plots. Alright, so let's explain. What pair plot does is that it shows a relation between different columns. So it basically creates a table of the columns by the columns. So as we can see over here, average area income. We have average area income over here, average area houses over second over there, first over there. Average area houses is the first over here. So average number of rooms, if you want to see, you can see average number of bed, average number of rooms as second over there, and average number of rooms is second over there as well. Now we what you can observe is that there are histograms at places where two similar columns intersect. So for example, average area income and average area income at the intersection, it forms a histogram. Why is that? Because they are not correlated. So it basically shows the values of the column in histograms. It does not we have no correlation, so there is no point showing the scattering of the data or the density of the data. What a scatter plot does is that it shows the density of the data and the scattering of the data, how much the data is scattered, and for which value over here, in this column, which is in the y, in which for which value in the y column is x, is which value for in the x column. So xy represents a column, this y axis represents one column, and x axis represents another column. Over here we do not have anything, so it just represents the value of one column. So there we go. So now let's create a histogram of the data in the price column. Now what I introduced to the concept of features in the machine learning lecture earlier, and here so we have 1 2 3 4 5 6, so we have 6 features, and we have to find a target column. So in this case the target column is the price column, and all these average area income, average area houses, average number of rooms, average area number of bedrooms, area population, all are the feature columns or the data which we will get. But the price is something which we want to find out. We want to predict the price, so that's the target. Alright, so if we want to see the variance. The variance is something I'll talk about in the statistical learning course again, and this we want to see how much does the data in the price vary, or what is the maximum. This is the maximum peak, as you can see, and this is the lowest peak. It's almost zero, and this is another lowest peak. This is probably the mean. Around, it's like half of this, whatever it is. Alright, so it shows a histogram of the data in the price column. We have to supply the data over here, and the column which we want over here. Right, what is this KDE? Yeah, this KDE shows the basic slope of the data, or the steepness of the data, something I'm going to explain in the statistical learning course, which will come in early December. Alright, df.correlation, CORR means correlation. It shows the relation of one column with another. Basically, it is one column divided by another column. So average area income with the data of average area income will be 1, obviously, because this data divided by this data is equal to average area income is equal to average area income, which means that if you divide both of them, you will get 1. Similarly, for every column we have 1 1 1 1 1 1 1. So there is no correlation between two similar columns, but there is a correlation between two dissimilar columns, because they are dissimilar. So you will get a quotient after division. One thing, why are we doing this? Yeah, because we want to see how related these columns are, right? If you want to see more if you want to visualize how related these columns are, you can see a heat map. What is heat map? So it grabs out correlation values, and this is an optional value. If you want this white markings and black markings right over here, you can do annotate is equal to true. If you don't want them, you can refer to the slave. You can read by referring to this label, then you can do false. So heat map here, or heat map, basically creates a table with the columns at one end, and with all the columns at one end and sorry for that, with all the 7 columns, all the 6 columns actually, and in the x and y direction both. So as we can see, in the intersection of two similar columns, we get 1 1 1 1 1 1 1, as the correlation is 1, but in the intersection of two dissimilar columns, we get a different value. Alright, and as you can see, the more dense the more the value is, or the lesser the value is, the greater will be its coloring or density. As you can see, this is almost these are the smallest values, so these are written in the blackish purple color, and these are the the highest values, therefore they are written in white color or almost peach color. Alright, if we grab df.columns again, I don't know why I've grabbed that, but it returns the columns. Alright, now it's just for us to copy basically from here. You can just copy paste and type it over here. We set the x, which is going to be our feature, to all the feature columns, and y, which is going to set to the target, which is assigned to all the target columns. So here we have price is something which we want to predict, therefore it's in the target columns. Also remember that we have to put the data, or else it won't understand. It will think that price is a string, or it's a list. Actually, y is a list. It will think y is a list, but if we want the values of price, we have to supply the data as well. Alright, now this is something which you have to memorize also. You don't want to refer to the documentation. This is from a scalar net model selection, import train test plate. So we have to we have done this multiple times in this machine learning course. So this is basically from a scalar net model selection, we will import train test plate. Alright, and then again the same commands, x train, x test, y test is going to be assigned to train test plate of x of the data, which is x and y. X is basically the first the target variable comes. So first target, so we can write over here. So first comes the target variables and second comes the feature variable. I mean, first comes the feature variables, second comes the target variables. Then we have set a test size of 0.4. We can change the test size. You can experiment with it 0.4, 0.2, 0.3. I recommend 0.4, which is 40% test size, 60% learning. So it's around 50-50, around like 50-50. But you don't want to do 50-50 because it is you get equal learning, and like the data has so much has trained or tested so much with 50% of the data that if you give a foreign data, it won't be able to analyze. Alright, or it won't be able to analyze with great accuracy. Alright, random state is something which means that your model will be same as mine. This is an optional statement, but you can do it if you want the model accuracy and model to be same as mine. Alright, so this is a new command, sklearn.linear model import linear regression. So this will import the linear regression model that we have, and from sklearn model linear model import linear regression. Alright, we have assigned LM to be the linear regression. It takes no parameters. Then we fit it with the data that we have, or the data which we want to train with, which is X train and Y train, because we want to test with X test and Y test. So X train and Y train, we are testing, we are training with it. Find if you want to find out the intercept, we can find it out. This is the intercept. Alright, coefficient, what is the intercept again? Intercept is the value at which x is y0, x is 0 and y is y has some value and x is 0. And linear regression, LM which is linear model in our case. So we have found the coefficient of the data, something I'm going to talk about in the statistical learning lecture. So x train or columns. Alright, x train or columns. So if you want to find out the columns, we are going to find out the columns, which will be equal to the columns that we assign to, and or the target or the feature columns. Now CDF is coefficient of data frame, which is which is an object where we have assigned pandas to data frame, and we have assigned the values lm dot coefficient comma x dot columns comma columns. So the data in the columns is lm dot coefficient is the columns. We have only one column. This is the index column. We have only one column, which is coefficient, and there we have the data lm dot coef of every column, or x dot columns for every for every coefficient of every data of every column of x dot columns. Alright, x test. This is x test. Y test, you want Y test, this is Y test. Now we will predict on X test. So let's predict. You can do it on Y test as well. So let's predictions is this. We can also try. You can also do one thing. You can print out the X test and see what the prediction is like. You can import from sklearn. I'm typing the command from sklearn dot. I've actually forgot myself because it is something, but something you'll see from the machine learning 2 lecture. I forgot now. Okay, so we create a scatter plot to see what is the variance of our data again. So we do it Y test comma predictions. So we test on X test. X test is equal to Y test, and Y test comma predictions. If we try to create a scatter plot out of it, this is Y test. This is Y test. This is X test. So let's see. Both are 20,000. So we can see that it's like almost the variance of the data is low. So the data our line passes exactly through the middle. We can, if we assume drawing a line through the mean of this data, it will be almost through the middle. There are some errors, there are some noises, but yeah, it is almost equal, or almost passes to the mean, but there are some noises, so it's not 100% correct, but we have done a very good prediction. So if we want to find out the noises which is equal to y-test minus the predictions, this is the disk plot of y-test minus predictions, or the histogram of y-test minus predictions in the price. From a scalar input matrix to mean absolute error. Alright, what is mean absolute error? So this is the notebook that you have got in the link in the description below, and this contains everything, almost everything. It contains better visualizations as well, more transparent, more clear. It contains heat maps. It contains comments about what to do and how did you do it. Alright, so this is the same predictions we got almost the same predictions. So let's look at regression evaluation matrix. So there are 3 common evaluation matrix for regression problems. Number one, we have mean absolute error, which is MAE. It is the mean of the absolute value of every error. So it is the mean of the values of the error. So y is the y-test in our case, and this is the y. This is basically refers to predictions, y predictions, but in this case it's equal to predictions. Now y minus y-test minus predictions will give us the noise, or the what do you call them? It will give us the noise, actually, noise, and we have to this is the basically the mean. It represents the mean. Now it will be equal to the noise, or the mean of the noise. Mean is something is an average, and something we're going to talk in the statistical logic lecture. Now you have mean squared error. Mean absolute error is the absolute value, which means absolute value means that if you have minus 25, it will be equal. If you take the absolute value of minus 25, it will be equal to 25, which returns basically the numerical value of the data without any positive or negative signs. Basically it's positive, actually. So it's a mean squared error is another regression evaluation matrix which returns the mean, which returns the beat of the square of the error, or it returns the mean. It returns the mean first. It first squares the error and then returns the mean. Alright, so that is mean squared error. Alright, root mean squared error, RMSE. So what is RMSE? Root mean squared error. It's the square root of the mean of the squared error. So how complex is that? Look, let me break it up. So first of all, we squared the error, then we find its first squared the error, then we find its mean. Finally, in the final step, you take its square root. So that's root mean squared error. So root of the mean squared error. So you can visualize this like it goes in the opposite way. First squared, then mean, then root. So there we go. So here first squared, then mean absolute error, first absolute value, then mean. So that's how you can visualize them. So if we want to find out the errors, here we go. That's the errors. It's almost equal to these values that we have. Not actually equal, not very equal, but it is equal. So if we do it, then we get this mean absolute error, y-test cover prediction. This is our mean absolute error. This is mean squared error. This is the square root of the mean squared error. Actually, I haven't done the same thing over here. So this is by the square root of this whole thing, which is the mean squared error. So that's where we'll stop for today, and thank you, and hope you learned something. So you'll get this notebook right over here, I mean in the link in the description below. So you can use this as a template, and you can build your own models here, and you can also save your models as I showed you using joblib, the matplotlib.extras, import job from matplotlib.extras, import joblib, and then store the file in the joblib. As we did, we created a joblib file which is binary. Actually, it is binary. So joblib is a binary file. If I want to show it to you, let's see. There's nothing. Alright, irisml1.joblib. If we open this file, we will observe that editing is disabled, saving is disabled. You want to see, you have to see console from Orals. Console is basically refers to the terminal. Now one thing I can show you this is by downloading the file, and let's see how we can open this, probably using Notepad. Alright, so let me open this using Notepad. Downloads. Alright, this file doesn't contain an associated app with it. Alright, let's see how I can open this. Notepad will be a good option. Well, this is the binary file that we get. It is gibberish actually. It is gibberish, but this is the binary file. This is a binary file. Joblib is a binary file that we have, and it is everything that is stored in our model. So it's basically our model. So that's this looks like alien language, your code's language. So that's it for today, and thank you for until next lecture.